Hey everybody, brand new topic. Let's get into some rotational variables and then talk about rotational kinematics. So let's say you have a wind turbine. And let's say the blade are just like this. Okay. We define some kind of angular position as, let's say, some angle theta, but it depends on some reference line. So say the reference line looks like this, and I want to know the angular position of this point of the turbine blade. So for example, 0. And then let's say the blades rotate 90 degrees, like pi over 2. So now it's over here. So let's say for this example, my initial was 0 degrees, which is 0 radians. And then it rotates over here. And so now it's at 90 degrees, pi over 2. Okay, so then there's something called angular displacement, delta theta, right? The change in theta, which is just, right, the difference. So angular position. This is angular displacement. So in this example, the angular displacement, pi over 2. But the numbers depend on the reference. For example, if I pick a different reference, let's say here, and then the initial angular position, let's say here is 45 degrees. So let's say pi over 4. And then now, when it rotates over here, now the angular position is 3 pi over 4. Right? So the values depend on where the reference is. Just like for gravitational potential energy, where you choose the datum. However, here, this is pi over 4, 3 pi over 4. The angular displacement is still pi over 2. So the angular displacement won't change. It's invariant with respect to your choice of reference. Okay, so that's angular displacement. And then new vocabulary. If you have delta theta over delta t, so your angular displacement divided by some time interval, that's called average angular velocity, omega. I'll just say average. So this is average angular velocity. So for angular displacement, this is radians. Angular velocity, radians per second. Okay, and then now let's calculus this thing. If you take the limit as delta t goes to 0, right, that's a derivative. So the derivative, this is called instantaneous angular velocity. You don't have to say instantaneous. If you say angular velocity, we know you mean instantaneous angular velocity. Right, so it's just the time derivative of angular position. And then, new vocabulary, if you take delta omega over delta t, so this is for angular velocity, this is called average angular acceleration. Average angular acceleration. So this would be radians per second squared. And if we use calculus on that, if you take the limit as delta t goes to 0, then that would be a derivative. So it's the derivative d omega dt, and that is called instantaneous angular acceleration. And again, you don't have to say instantaneous. If you say angular acceleration, we know you mean instantaneous. And this is a Greek letter omega. This is a Greek letter alpha. So everything together, let me just rewrite it. There's angular position, theta, angular velocity, omega, which is just the time derivative, and then angular acceleration, alpha, which is the time derivative of angular velocity, right? And then since this is the derivative of this, and this is the derivative of this, angular acceleration is also the second derivative of angular position. Okay, so if this looks super familiar, this is basically the angular version of things that move linearly. Like if something is moving linearly in the x direction, this could be position x, velocity, dx dt, acceleration, dv dt, which is also the second derivative of position. Right, so hopefully it looks super familiar. It also means everything you've ever practiced for kinematics, going in straight lines for translation, all that information is still useful because you now apply it for things that are rotating. Okay, and then specifically for constant angular acceleration. So this is analogous to when we're discussing if you have constant linear acceleration. For constant angular acceleration, you see right here for angular velocity and angular acceleration. Let me just write that. Let's say you want to solve this for omega. Then you can move this on this side, separation of variables, and then integrate. But if angular acceleration alpha is constant, we can move it out of the integral like this, and then from somewhere to somewhere, from initial to final like this, t minus t naught. If I say t naught is 0, and move this on the other side, and here we go. This is angular velocity if angular acceleration is constant. And then for here, let me copy this one over here. If you want to solve for angular position, let's move this on the other side, separation of variables, and then integrate. This goes there, so let me just write that. Okay, and let's integrate this over time from somewhere to somewhere. Let's say t naught starts at 0, so let's integrate this. Omega naught t plus 1/2 alpha t squared, assuming this is constant. And so what we have is this, which should look super familiar, right? For something moving in a straight line, say in the x direction, it would look like this for constant ax, right? Looks similar. And velocity, right? Looks familiar. So again, everything you've ever done for kinematics when things are moving in straight lines, it also applies when things are rotating. So you basically just doubled all of your knowledge just right now. Okay, and then how does one relate to the other? Linear systems and rotating systems. So let's go back, like if you have a circle. If you, let's say, start over here and go over here, how far is this? Right, so if we have some radius r, and this is some angle theta, let's call this path length over here s. So it's along this curve, some arc length s. How does it relate to the radius and the angle? Like this. Right? For example, imagine if you went all the way around the circle, 2 pi radians. Right? Then what is the arc length? The circumference times r. Right? That looks familiar. The circumference, 2 pi r. This is the arc length. This is the angle. That's the radius. Okay, so maybe that's like a good mnemonic device to remember this formula. And now, let's assume constant radius and take the time derivative. So take the time derivative of that side. R is constant. Take the time derivative of this. So what is that? That's velocity, like meters per second. What's that? Angular velocity, radians per second. So you see the relationship between linear velocity and angular velocity is just like this, it's the radius. The relationship between some arc length, meters, and some angle, radians, just like this. Okay, now let's take one more derivative of this for constant radius. So dv dt, d omega dt, what is that? That's acceleration, but only in the direction of the velocity. So actually tangential to this curve, tangent to the curve. So it's the tangential component of acceleration, this. And what's that? Angular acceleration. Okay, so this is the tangential component of acceleration. This is meters per second squared, and this is angular acceleration, radians per second squared. And then what is centripetal acceleration? You remember it's v squared over r. But look at v. V is r omega, right? So let's plug that in right here. R squared, omega squared over r. And then see there's r squared over r, so let's get rid of that. Okay, so this is centripetal acceleration in terms of angular velocity. Okay, so this is the relationship. This between linear and angular. Okay. So how about some quick example? And then to use the formulas is pretty straightforward, so I can do some examples on other videos, but this is the introduction to all rotational kinematics. Okay, so I'll see you on the next video.